galaxy with enormous amounts of material falling in, heating up, making a lot of light, and a small amount of it being shot out as jets and as globules, just the way the gravity interacts in these processes. So what we show here is a spectrum that was taken in 1997 in the blue line with the Goddard high-resolution spectrograph, which was the spectrograph on board Hubble at that time, and in 2009 with COS. And you can see the spectra look pretty much the same. One of the things we wanted to do was to calibrate the instrument with this observation and make sure it was working properly. But this observation took only 9% of the observing time that it took in 1997. So again, we've become a much more powerful instrument and able to get much more data. Also, that's the entire spectrum from 1997, but that's only 1/8 of the spectrum that we collected in 2009. It runs off the page 4 times as long in both directions. One of the interesting things to note, as denoted there by the red mark, is that one of the features in the spectrum in 1997 is now absent. This was a blob of gas blown out by the black hole that the light was passing through that has now since moved out of the way, and in fact, it is no longer visible to our instrument in this time. And I just think it's sort of interesting to note that we're looking at something millions of light years away, the size of a galaxy, and yet over 12 years we can see how it's fundamentally changed. And that the cosmos, even though it's billions of years old, still operates on human timescales. I'll just wrap up by saying that the goal of COS was to build an instrument 10 times more powerful than the previous capabilities. And I'm pleased to announce that we've succeeded in that goal. And I'm looking forward to getting lots of observations in the next coming years. And I agree with Dr. Weiler that we've got a good 10 years to go. But with that, I'll pass it on to Dave Leckrone, Senior Project Scientist for HST.
Thank you, Jim. Good morning. Bob and Jim have described some of the early observations acquired with our 2 brand new instruments, which extend Hubble's observing power by factors of 10. And these are very high technology instruments and are performing superbly in both cases. Another unique aspect of this mission, however, was the attempt to repair 2 very valuable instruments, very valuable assets that had failed electronically. Space Telescope Imaging Spectrograph, which failed in 2004, and the Advanced Camera for Surveys, which failed in 2007, in both cases because of electronic short circuits. So a bold initiative was undertaken and involved tremendous effort on the part of the crew working with our engineers and designers on the ground. A bold initiative was undertaken to attempt to repair both instruments. And I agree with Ed, going into the mission, we realized we were attempting 2 repairs. If we could get at least one of those to be successful, then that would be a good outcome for the mission. What we really never dared dream of was the possibility that actually both repairs might work. So I'm here to report to you today that both are working splendidly, and I'd like to show you observations taken since the servicing mission with both of the repaired instruments. So if I may have the first graphic, please. Okay, what you see here is a representation of 2 different observations. On the left, there's a picture of an image taken with Hubble many years ago of an exploding, a very highly active star called Eta Carinae. And this star is actually 2 stars, very massive stars orbiting around each other. In some cases, one's in a highly elliptical orbit around the other, and they come close to each other. These stars are so massive, they burn their energy very rapidly, and they're not going to last very long. Their lifetimes are short. Sometime within the next 100,000 years or so, this system of 2 very massive stars is going to blow up. It's going to become a massive supernova, possibly a gamma ray burster. It's going to be an intensely energetic object, and it's only 7,500 light years away from the Earth. The nice thing is, at that distance, we think we're protected, so we don't have to worry too much about the impact. But astronomers within the next 100,000 years or so are going to have the opportunity to observe, and ordinary people are going to have the opportunity to observe an extraordinary flash of light in the sky and to study it. Now, what you see coming off to the right there is the new observation with the Space Telescope Imaging Spectrograph. There's that long dark slit that you can place over the image of the object, and you can collect light point by point along that slit. And at each of those points, the light is spread out into its component colors, and you can see a spectrum that corresponds to each spatial point along the slit. And in this particular case, this was taken last June. The 2 stars had just passed through their moment of closest approach, and there was a lot of energetic activity happening. I talked to Mike Massimino and the rest of the crew before the mission, and I said, one of the things we really need to do, we've been monitoring this baby. It's so dynamic, it's so energetic. We've been monitoring this since 1997, and then we had to stop in 2004, and we haven't been able to continue the story. And so now, in fact, thanks to you guys, we're back up and running, and the story continues, and we can continue to monitor how this star is changing over time and look at its dynamics and get some understanding of how someday in the future this is going to become a really spectacular fireworks show in the sky. So that's the Space Telescope Imaging Spectrograph story. The next image, please. Okay, this is a cluster of galaxies called Abell 370. It's about 5 billion years away from us. It's a group of galaxies, large and small, that are all gathered together and held together by gravity. In particular, they're held together by the gravity of dark matter that's within the cluster. It's not just the luminous matter in the galaxies you see, but there's about 5 times more material that's cold dark matter that we don't really understand what it is. But all this material together exerts enough of a gravitational force that it can bend light, as Einstein predicted in his general theory of relativity. So the light from galaxies that are beyond this cluster, the light rays are bent as they pass through the cluster and come to us, and they're focused like a crude lens. So this is called gravitational lensing. This particular cluster was one of the early examples of this that astronomers came to understand as an illustration of how Einstein's gravitational lensing works. And in fact, you see that long, bright arc up in the upper right. It was known back in the 1980s that that was an example of a gravitational lens. The power of Hubble, though, is that we can see incredible detail in that arc. So if I may have the last image, and it's rotated 90 degrees, and we've zoomed in. So this is really fascinating to me. I've never seen anything quite like this before. This is the gravitationally lensed image of a single spiral galaxy that's like twice as far away from us as the intervening cluster. And so, and we call this the dragon just because it kind of looks cute in that sense. But on the left side, you see an image of the galaxy, quite detailed with a lot of color information in it that we'd never seen before we had taken this image. And then up on the upper right, you see an image, the tail, so that's the head of the dragon, and then the tail in the upper right, which is an image of the very same galaxy. And in between, you see the stretched out band of light, each which really is comprised of stretched out images, 3 or 4 additional images of this same galaxy. And this is what, I mean, it's just remarkable what gravitational lensing can do. And in particular, this is nature's telescope. This is taking the power of Hubble and enhancing it tremendously with gravitational lensing so that we can actually study detailed structures in galaxies that are incredibly far away. Another thing I can say is we don't see, normally you might see a counter example of this on the other side of the cluster. You don't see that, and that tells us the very particular special way that the dark matter is distributed within that cluster. So I'm proud to report that prior to this mission, with our instrument failures, we were down to 3 operating channels, instrument channels on Hubble. Today we have 13. We have 6 fully operating instruments today. I say fully operating. One of them, the Nick Moss, has just come back online. We're still in the process of checking it out, and it'll begin its science program a little bit later. But in addition to the instruments, I'm not able to report any failure or problem on the spacecraft itself. So I know it was a tough mission, and I know there are a lot of travails, but somehow, some way, you guys pulled it off. You just refused to say die, and you kept going. And we have a fully functioning, beautifully operating Hubble Space Telescope today. So with that, I'd like to turn it over for some closing comments, or nearly closing comments, to Heidi Hamill.
Thanks, Dave. It is a wonderful coincidence that Servicing Mission 4 occurred in 2009, because as